Good evening, students. We are doing today 2022 A-level structured essay 1 and then 2023 A-level structured essay 1. Okay. So in our last week discussion also, we could do 2019 and 21 A-level structured essay. So doing this structured essay will help you to get ready with that compulsory structured essay that will be there in any A-level paper. This one basically asking about the unit 1 and unit 2. We will see how these 2 years have asked the questions about those lessons. So I'll share with you the 2022 A-level structured essay question. Like any other structured essay, the first part is coming from the short questions. So state whether the following statements are true or false on the dotted lines. Reasons are not required. So the first statement they're asking, the Lyman series observed in the emission spectrum of atomic hydrogen lies in the ultraviolet region of the electromagnetic spectrum. So they're asking whether the Lyman series is there on the ultraviolet region. So we all know that is so obvious that statement is true. Okay. So what are the things we have to remember regarding hydrogen emission spectrum? So if I summarize the points by just verbally, I can say this first point. Okay. So hydrogen emission spectrum, strong evidence to suggest the existence of energy levels. Bohr actually used the energy level concept to explain the emission spectrum. Understand? So basically, between energy levels, electrons are transferring. That is what happening during this emission spectrum. Okay. So electrons that jump to the upper energy levels are coming back to the lower energy levels by losing the energy, right? So the Lyman series lines are responsible for the jumping to the first energy level. Okay, because first energy level and the other energy levels are having considerably higher energy gap. Because of that, the energy released is also higher. Therefore, Lyman series, all lines will belong to ultraviolet region. Understand? So we can put a small diagram to explain that one. Will be a nice thing to do. So for the first question you can say like this. Now, these are our energy levels. Like that we can say. First energy level, second, third, fourth, and fifth. Like that we can say, okay, some energy levels. You can see the energy gap between the first and the second is a very higher value than the others, right? So the electrons that are jumping for the first energy level, we call them as Lyman series. So L1, L2, like that. So these are belong to the UV region. And we can show Balmer series for the comparison sake. These are the first three lines of Balmer series, which is red, green, blue, and there will be another line coming from the sixth energy level, which is colored as violet, right? You can see their lengths are shorter than the Lyman lengths, no? So you can understand these are falling to the visible region, and therefore Lyman series are having higher energy gap. Okay, so therefore we can say our first statement is true. Okay, now my first statement is true. Right. And then look at the second one. There are only 10 electrons in calcium atom with the azimuthal quantum number L equals 0. Calcium atom, azimuthal quantum number. So there are two things. So first of all, we need the calcium electronic configuration, right? Calcium electronic configuration. So calcium is having atomic number 20. That means there are 20 electrons with calcium. Okay. So then you can write the electronic configuration starting from 1s, 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. That is the calcium electronic configuration. You can check. There are 20 electrons you can find. Okay. And then here they are asking about the L equals 0. Azimuthal quantum number L equals 0. So there are 4 quantum numbers. Okay. N. We have 4 quantum numbers. N, L, ML, and MS. N, L, ML, and then MS. Okay. So N represents the main energy level. Main energy level. L stands for the sub energy level. sub-energy level. And Ml stands for the orbitals in the sub-energy level. And Ms stands for the spin. Okay. So in Bohr model, they says electrons are moving in energy levels, no? Right? But when we go to the our A-level atomic model, quantum atomic model, we no longer can say electrons are moving in certain path or energy level. So electron location is somewhat random. Okay. So therefore, we express the location of electron using a probability cloud. You can go through the recording also if you want, Lamai, right? In case you have forgotten these things, right? So electrons are moving in probability cloud. Right? So those probability clouds we call as orbitals. Remember orbitals. So those orbital types are expressed in the sub-energy level, L, azimuthal quantum number. So we can have S orbitals, P orbitals, D orbitals. Like that, there are several shapes for those probability clouds. For example, S, you have a spherical shape. P, you have a dumbbell shape. D, also you have several shapes, right? So, however, you can see the probability clouds are different. So, for the L value, 0 comes for the S sub-energy level. And for the P sub-energy level, you have the value 1. For the D, you have value 2. That's how we get the quantum numbers for the sub-energy level. Okay, or you can say orbital types. Orbital types. Okay. So they are here asking azimuthal quantum number L equals 0. So L equals 0 means S sub-energy level. You can understand L equals 0 means S sub-energy level. Sub-energy level. So in S sub-energy level, how many electrons are there in our electronic configuration? See, 1s2, 2s2, 3s2, 4s2. You have how many electrons? You have 8 electrons, not 10. Understand? So you will find only 10 electrons. Is wrong. Okay, you will find only 8 electrons. So therefore, we can say second one is wrong. So this one was true. This one is now going to be false. Now look at the third question. The number of Lewis dot dash structures or resonance structures that can be drawn for N2O. They are asking the resonance structures of N2. N2. So N2O, the central atom is going to be one nitrogen. And then there will be, we can put 2 double bonds. And there will be a negative charge and positive charge. And we can draw another structure by putting a triple bond between 2 nitrogen. Then you will have this oxygen negative charge. And here positive charge and lone pair nitrogen. And then you can draw another structure by putting a triple bond between 2 oxygen and nitrogen. Then oxygen will contain a positive charge. And the central nitrogen will also contain a positive charge. And the peripheral nitrogen will contain -2 charge. So like that, you have 3 structures. So actual N2O is a resonance hybrid of these 3 structures. So telling that they are having 3 resonance structures is correct. So number of Lewis structures can be drawn for the N2O molecule is 3. That one is true. You can draw 3 structures. But what about the stability of these? I'm going to ask you a question. Let's label them as ABC. What is the most stable resonance structure? Or we can ask which structure contribute mostly to the hybrid? What do you think? Yes, very good. So B is contributing mostly. So this one is the most stable structure. And then you have the next one. This one is the next stable structure. And this one is unstable. Okay, so this one we can say less stable. Like that to your review, Lama, you can add this discussion about the resonance structures. Okay, good. So now we can go to the fourth one. So it's asking about the periodic properties. Okay, periodic properties, fourth one. Among the second row elements in the periodic table, fluorine has the largest negative value for the electron gain energy. So what do you think? If you get the second period elements starting from lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, right? So this fluorine, when it gains an electron, it do this reaction F minus it turns to gaseous F minus, right? So this one will happen readily. Okay, so it is releasing a relatively larger energy than the other second period elements. So this one is true actually. So we have a statement for that one. We have a statement for that one. So if you take the third period, okay, third period, the highest electron gain energy negative value will be there for this chlorine. And if you take the next period, fourth period, that value will be there for bromine. So like that in any given period, okay, any given period, highest negative value for the electron gain, or we can say the element that most likely to take the electron is the halogen. Most exothermic, or you can say highest negative value, or you can say most electron affinity, most exothermic. This one is a electron gain in a given period is shown by halogen. Okay, so like I said, in the third period, halogen will be the highest, chlorine. So then you can compare between halogens also. Chlorine, fluorine, bromine, and I hope you remember this one. This was very popular in our paper discussions, isn't it? So chlorine is the one with the highest electron gain negative value, or you can say the most affinity is there for the most likeliness to the electron is there for chlorine. Okay, it's not fluorine because fluorine is what? It is too small. The problem with the chlor F is it is very small. But in the other hand, Cl is having some optimum size. Remember? And others, bromine and iodine are very large. That's the problem. Then nuclear attraction is less. Here, repulsion of electrons are high. But chlorine is the one with the optimum size. Optimum size. Yeah, in earlier one of you asking a question why A is not the most stable. The reason is it is having the negative charge on nitrogen. Existing the negative charge on more electronegative atom help to become this structure stable. Fifth one is asking the boiling point of argon and chlorine. Boiling point of argon is higher than that of chlorine. That is going to be wrong. That is false. Why? What is the problem? So argon is a monoatomic gas. Chlorine is a diatomic gas, ClCl. And both are nonpolar. So these nonpolar molecules, they exist London forces as the intermolecular interaction between them. If their intermolecular interactions are powerful, they will have higher boiling point. That means if their attractions are better, then it is very difficult for us to boil them, turn it into gas. It's very difficult to turn them into gas. Okay. But so which one will have the better interactions or which one will have the better London forces? So how do we decide that? We can decide that depending on the factors that affect the strength of the London forces. So London forces strength depends on three things. Remember, we can say the size. When the size is larger, that means when it is having higher mass, it will form more London forces because it have more surface area and more electrons. Okay. And then if the shape is kind of linear, okay, if it is having no branches, if it is without any branch, then again the boiling point is high. That is purely applicable for like organic molecules. It is not going to apply here. Okay. And then the distance. If the distance is lower, London forces will be strong. Right? So here, but the factor that is applying is the size of the molecule. You can see, we can compare the size by checking the relative atomic masses or relative molecular masses. So argon atomic number 19, so 18. So at least 18 times 2, greater than 18 times 2, you will have molar mass for the argon. So this one is 35.5. 35.5 into 2. That means 71 is the relative atomic mass of this one. So therefore, London forces will be higher in the Cl2. Therefore, Cl2 will have a higher boiling point. Then we can come to the last one. Neon has the highest first ionization energy among the noble gases. Helium, neon, and argon. Yeah, that's wrong. Again, why? Ionization energy highest element of the whole periodic table is helium. First ionization energy highest for helium. Why? because it is having the noble gas configuration, which is very stable, and it is having the smallest atomic radius also. Then very difficult to remove electrons from helium because of the higher nuclear attraction and stable electronic configuration. So ionization energy, first ionization energy will be highest for helium, not neon. Okay, and remember the order. Remember the order for the first ionization energy. I think I gave you this one few weeks ago. Anyway, helium is the highest one. Then you have neon. Then after that, it's not argon. It's not argon. It is going to be fluorine. That's a special point. Okay. Then you have argon. Then not krypton. It is nitrogen. So krypton first ionization energy will be lesser than that of nitrogen also. Remember this one. These are the ones with highest ionization energies. Now you can see between what happened to the fluorine and nitrogen. Their nuclear attraction overcome the stability gained by the stable configuration. Yeah? So that is the reason for having higher first ionization energy. So fluorine is having a greater nuclear attraction than argon. Okay, so like that, try to understand. So I hope it is crystal clear for all of you, right? So most of the things we have discussed in our previous classes. So don't wait until there is a term test or something. Study now and get better. Now let's go to the usual Lewis structure part of the question. So they have given us a skeleton. The skeleton of the molecule containing only elements NFS is given below. Okay. Draw the most acceptable Lewis dot dash structure. Right. So, like we decided last week, we are going to use our practice for these questions. If you want, you can go with the Lewis method, but it is some kind of time consuming. Right now, we have drawn lots of Lewis structures, and I think we have that practice. Okay. So, in that case, we know fluorine, when it is coming as the peripheral atom, it's always making a single bond and keeping the three lone pairs. Fluorine always comes as the peripheral atom. Okay. When normally fluorine and other halogens comes as the peripheral atom, they keep three lone pairs and makes a single bond. They keep three lone pairs and makes a single bond. Like this. Okay, then we have to think about a way to complete the octet of nitrogen and sulfur. Okay, so nitrogen right here should keep 5 electrons now to have no charge. Then this is the suitable way. Putting a double bond and putting a lone pair. Then in that case, nitrogen will not have any charge. So let's say the other possibilities, if you put two lone pairs, okay, then you can put two double bonds. Or like that, you can do something. In each case, it will have a charge. These cases are unstable for nitrogen. It's not good. So having the double bond and a lone pair is the best option. And you obviously you can't put a double bond with fluorine. Then you have to do it with sulfur. Okay. Now, if you check sulfur in this case, right now it is having a charge. It is having a +2 charge. But this molecule, if they say molecule, then it is having no charge. No? So therefore, putting a charge on sulfur is wrong. So to cancel the charge on sulfur, what should you do? You have to put a lone pair. Understood? So then there will be 6 electrons on sulfur, which making it is neutral. This is the structure of the Lewis structure of the molecule. And then it is asking us the shapes and the oxidation numbers of these nitrogen and sulfur. Oxidation numbers and shapes. First of all, they are asking the shape. Now, if you check this nitrogen, you have 3 VSCPR units. A lone pair, a double bond, and a single bond. So 3 VSCPR pairs. We consider double bond as one repulsion unit. So anyway, there are 3 units. So out of that, you have one lone pair. So you have one lone pair. And you can say now, therefore, bent or angular or V shape is the shape of the molecule. And then you can do the same thing with sulfur. Sulfur is having 4 repulsion units. Therefore, it is having tetrahedral electron pair geometry. But it is having one lone pair. No? Therefore, it will have trigonal pyramidal shape. So those are the shapes of these two uh, atoms around the atoms. Okay. Now they are asking the oxidation number. Then you can mark the dipole moments. Mark the dipole moments. Okay. So fluorine is more electronegative. Therefore, fluorine will pull one electron away from nitrogen. And when you compare nitrogen and sulfur, nitrogen is more electronegative. And if you consider sulfur with fluorine, fluorine is more electronegative. Now, you can write about this nitrogen. So we can say, if you look at the arrows and we can say, lost one electron partially and gained two electrons partially. So the resultant is gaining one electron. So gain one electron means negative one oxidation state. Then you can look at this sulfur. It is losing four electrons to the surround or lost four electrons. That means its oxidation number is plus. Then the resonance part. And they're asking to draw three more resonance structures for this molecule. If the central atoms are CNO, carbon, nitrogen, oxygen, there is a rule. No? We can definitely say how many structures we can draw. Because by changing the 5 bonds, we can get the total possible structures. Okay, so here also the central atoms are nitrogen and oxygen. That means it will form a fixed number of resonance structures by simply changing the location of 5 bond. What are the structures going to be? So we can put this 5 bond into 3 locations. No? You can see the oxygen, other oxygens are making single bonds. No? To those places, I can put the double bond. So therefore, there will be 3 structures. NO4 minus. No? So therefore, should be overall negative charge. Okay. And then we can draw several skeletons and put the 5 bond to the possible location. I can place the double bond here, here, and here. So that means there will be 3 structures. Now, without violating the octet, I have to place the lone pairs. So how many lone pairs are there in the original structure? 3, 6, 10. 10 lone pairs were there, no? So I have to place those 10 lone pairs here. So 1 and 2, 3, 4, 5, plus, minus, 6, 7, 8, 9, and 10. A negative charge. And then this one, negative, negative, 9 pairs, plus 1 pair, plus. Now that one is going to be unstable. And then this is structure. That is 1 pair on nitrogen. Positive charge on nitrogen. So these are both equally stable. And this one is most unstable. Because you can see positive charge on oxygen. And there are similar charges on adjacent atoms. There are 2 problems. So therefore that is most unstable. But this one is also somewhat unstable because of the positive charge on oxygen. But there are no adjacent equal charges. Therefore, this one is a little bit better than C. And then we have the usual table. And I'll show you that part also. So there are 4 resonance structures. Okay, even though they are having different stabilities, every structure contributes to the hybrid. Every structure contributes to the hybrid. Even the most unstable structure contribute at least a smaller percentage. First, they're asking the number of VSCPR pairs. VSCPR pairs. Now, around this carbon, you have 3 bond pairs. So, you have 3 VSCPR pairs. And around this nitrogen, you have again another 3. Because lone pair, double bond, and single. In the third nitrogen, you have 4 VSCPR pairs. Here, you have 2 VSCPR pairs. Okay, so depending on the number of VSCPR pairs, we can decide the electron pair geometry. So if they are having 3 repulsion units each, it will be having trigonal plane. So don't draw triangle, okay? Right? Trigonal planar in the space. Okay, so trigonal plane. And if it is 4 repulsion units, tetrahedral. This one is going to be linear. Those are the electron pair geometry. So depending on the number of lone pairs, the shape is going to be changed. So shape. This one is trigonal plane. because there are no lone pairs. Here you have one lone pair, so it's going to be bent. And this one is also going to be bent. Or angular, don't write linear. Right? That's a common mistake that most of you are doing. That's wrong. Even though we draw lone pairs in either sides, it's actually they are like in water molecule. Lone pairs in the same side, remember? So therefore it's going to be bent. Hmm? And here shape is linear. And then hybridization is also very easy. If there are three repulsion units, trigonal planar, it is sp2 hybridization, sp2 and tetrahedral sp3, linear sp. We can say why it is sp also like we did last week. So when this N4 nitrogen undergo sp hybridization, only s orbital and one of the p orbitals are hybridized. So nitrogen keeps two p orbitals without putting to the hybridization. That means nitrogen has two unhybridized p orbitals. So what's the purpose of keeping those two unhybridized orbitals? Because then after that nitrogen can make 5 bonds with the other nitrogen at the end. To make 5 bonds, right, you need unhybridized p orbitals. That's why this nitrogen, N4 nitrogen, is keeping two unhybridized p orbitals. Understand, Naman? If you remember, last week we did another question, 2019. In there, I explained these 5 bonds are perpendicular to each other. Remember, 5 bonds are perpendicular to each other also. Remember that, huh? It's a good thing to know. Anyway, so the same thing can be applied for these sp2 things also. Now, they undergo an sp2 because they want to keep a p orbital to make this 5 bond. That is the reason. They are asking about the orbitals that participated for the bonding. So H1 and H and C1, hydrogen and C1. Hydrogen always one s atomic orbital is there. For the C1, you can say sp2 hybrid orbital, or you can just say sp2, that is enough. And then C1 and N2, C1 sp2 hybrid orbital, N2 sp2 hybrid orbital. Then N2 and N3 sp2 sp3. Okay, N3 is sp3. So N2 sp2, N3 sp3. Okay, then N3 and N4 sp3 sp. Right, sp3 sp. Then the last one, N4N, N4 and N, the last nitrogen. You can say N4 sp hybridized. Okay, and then last nitrogen, either you can say sp or you can say 2p. The last nitrogen, you can say 2p also. So the peripheral atoms, you can consider either hybridized or unhybridized. Then they ask in the p orbitals participated for the 5 bonding. They all are 2p, 2p, 2p. The sixth question for the C1 and N2, 2p, 2p orbitals of carbon and nitrogen. And for the N4 and other last nitrogen, 2 5 bonds are also made between 2p orbitals. So you have write 2p, 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 2p. So don't write 2p for every 5 bond. On the last week also, one of our students asked that question. So you can't write 2p for every 5 bond. Huh? So then refer my 2018 structured essay recording. There a 5 bond was made with d orbital. That's a good thing to study. Now look at the 7th one about bond angles. These 4 labeled atoms, they are asking the bond angle around them, and then later they are asking the electronegativity for the 3 nitrogen atoms. Okay, so let's do that part. So about the bond angle. Now, this one was having trigonal plane electron pair geometry. For the trigonal plane, absolute bond angle, or the ideal bond angle is 120. Okay, so there are no lone pairs, so you can keep 120 bond angle. But here you have a lone pair. So lone pair kind of pushes more. Because of that, we are subtracting for one lone pair as a kind of habit. We subtract 2.5. So then it's going to be 117.5, the bond angle. Here you say bond angles. This one is 120. This one is 117 point. 117, 118. They will give marks for any. Yeah, don't worry. And then here you have 2 lone pairs. Like I said, they are pushing more. So bond angle decreases rapidly from, we have to subtract 109.5 Subtract 2.2 of the 2.5. That means 5 degrees. So it's going to be 104.5 around the that is the angle given for the water molecule. And this one, since it is SP, we can say 180 degrees. Linear electron pair geometry, 180. So these angles are not exactly the same values. Huh? They're asking you for the approximate angles. No? So telling this one will be in. Then they're asking the electronegativity of these three nitrogen atoms. Electronegativity. So remember our discussion? To compare electronegativity, we have to follow scope. S percentage, charge, oxidation number, and peripheral atom electronegativity. So first priority is given for the S percent. You check the S percentages of these. That will be enough, no? Yeah, that will be enough because you can see 2 repulsion units, 4 repulsion units, and 3 repulsion. Okay, so S percentage of this one is 50%. This one is 25%. This one is 33.3%. So depending on the S percentage, we can easily get the electronegativity. So least electronegative one will be the N3. Then you have N2, and highest electronegativity will be there for the N4 because it is having sp hybridization with 50% S character. So you don't need to go to the charge, oxidation number or anything. Just looking at this S percentage is enough. Yeah, in this question, this is a good one. They are asking you to arrange these given properties, given entities according to the properties in ascending order, smallest to highest, smallest to highest. So here, the ionic character, you can simply say it depends on electronegativity difference, delta En. If delta En is higher, ionic character is also higher. Okay, you can see the same cation is there. So depending on the anion, ionic character changes. Okay, so here the anion, fluorine is there. That is electronegativity fluorine, chlorine, bromine, iodine. This is how they are changing, no? Right? So electronegativity. Therefore, delta En also will be higher for calcium fluoride. So they are asking the ascending order of the ionic character. So answer for this question. Answer for this question will be calcium iodide, then calcium bromide, calcium chloride, finally calcium fluoride. It's the highest ionic character because this one is the one with the most electronegativity difference. Okay, most electronegativity difference. Then the bond angle is asked. Bond angle is asked. ClF5, ClF2 plus, and ClF2 minus. So in these cases, Lama, what I recommend is not to draw Lewis structures usually, but right now you are still at the very early stages now. So it's okay to draw Lewis structures. I also explain using Lewis structures, but when you go to the A-level exam, try to get the structure within your head. It will give you the answer fast. Okay, so I'll tell that one at the end, but anyway, let's get the Lewis structures and first get some answer for this one by any method. So ClF5 around chlorine, you have 6 repulsion units, right? Yeah, 4 fluorine atoms. So it is having square pyramid. So bond angle may be approximately around 90 degrees. Can't say exactly because there is a lone pair. It will have definitely some effect on the bond pairs. And ClF2 plus, ClF2 plus, F2 plus. So there are 7 electrons for fluorine. If you subtract 2 for the 5 bond and 1 for the positive charge, you will have 4. That means 2 lone pairs. 2 lone. 2 lone. So it's going to be like this. Just like watermelon. Plus. And Cl of 2 minus, you will have 3 lone. So it's going to be like this linear. Sun is somewhere around 104.5 degrees. The sun is 180 degrees. So bond angle like that we can say. I forgot to mention the shapes and geometries of this one. This is angular shape. This one is linear shape coming from the regional bipyramidal geometry. Understand, Naman? So what is the ascending order of bond angles? Kind of a tricky one, no? Yeah. So the given order is the ascending order. CLF5, CLF2 plus, and then CLF2 minus. Then they're asking the ionic radius. Sodium, sulfur, chlorine, and potassium. When you have potassium, then you have chlorine. Largest value will be there for the sulfur. So this is the one. So these three are isoelectron. These three are isoelectron. So when the number of electrons are same. Okay. And here potassium plus will have, we can write the protons on the top here. 19 protons. This one is having 17 and 16 protons. So when the number of protons are higher, its size is going to be lower. Okay, and our sodium is the lowest because it is having only 2 energy levels. First energy level and second energy level. So, but potassium is having 3 energy levels. First, second, and third. Understand? Sodium plus, if you write the configuration, we'll understand. 1s2, 2s2, 2p6. 2 energy levels. So in the size, or you can simply say ionic radius or whatever the radius increases downward the group. So obviously, so potassium will have a higher value than sodium plus. And then look at the carbon-oxygen bond length. Carbon-oxygen bond length. So we're going to draw them. First one is carbon monoxide. The carbon-oxygen triple bond is there. Then you have carbonate. I hope you remember the discussion about bond lengths. Now, even though we draw a double bond and a single bond separately, actual structure will have the partial pi bond thing, no? So, if I draw carbonate properly, this is the hydrogen. So, bond order is 1.33. And then you have HCO2 minus. No, this one, no? Kind of tricky to draw. Anyway. And this one will have, we'll go structure separately. This is the hybrid, 1.5 bond. And then H2CO, you have a double bond. And then CH3O, which you have a single bond. You have a single bond. So single bond, double bond, triple bond. We have to start from the smallest. No? Smallest is carbon monoxide, the triple bond. Then you have the pure double bond between this one, H2C. Then you can go to the partial pi bonding thing. 1.5 is a larger value, no? So this is going to be the lower one. HCO2 minus. And then you have CO3 2 minus 1.33 bond order. Then you have single bond, CH3O. CH3O. So this is the order for the bond length. Draw the resonance and get the idea about the hybrid and bond order. Then you can get the answer. It's a good question. Huh? It's a good question. So last few questions, they are trying to start you with the time. And look at the last one. First ionization energies, lithium, nitrogen, fluorine, magnesium, and phosphorus. Draw the graph actually, sir. lithium, nitrogen, chlorine, then you have magnesium, then somewhere here below nitrogen you will have phosphorus. Okay, now you can compare the relative locations. Relative location. Okay, magnesium will be higher than lithium. So first ionization energy lowest is therefore the lithium, then magnesium, then phosphorus, then nitrogen, finally fluorine. And it's also a good tricky question. I mean, they have checked whether you know with the difference between lithium and magnesium. Okay, so that is the end of the 2022 A-level structured essay. So I will show you the marking scheme now. So first statement was true, second one was false. Yeah, true, true, and false, false. I hope it is okay. And this is the Lewis structure. You can see how 5 marks are given. And angular -1. They are requesting you to put the sign. Without sign, no marks because it is -1 in the resonance structures. Actually, no need to draw the initial one. Nah? You can see they haven't given any marks for the initial one also. Drawing the 3 structures they have asked is enough. Yeah, this one is okay. This one is also okay. I said earlier you can put 2p and then the bond angle, see the range. You can write any number, okay. Electronegativity also okay. We did that one. Then these are the final answers. High electronegativity difference affect the ionic character. If electronegativity difference is higher, the bond will have more ionic character. And then let's see this bond angle thing. Yeah, it is correct. And the ionic radius also correct. Bond length also correct. And then finally the ionization energy. That also. Quickly, we will go through the 2023. Yeah, of the following sets of quantum numbers, we have given you 3 sets, M, L, and ML values. 2, 1, -1. And the second set is 3, 1, plus 2. Third set is 4, 3, and -3. Okay, so they are asking not acceptable quantum set. So the first 2 quantum numbers are telling you where this sub-energy level going to be. So this one, 2, 1 is 2p, 3, 1 is 3p, 4, 3 is 4f. So then there is no problem, no? 4f is there. Then what is the incorrect one? You can see the second one. So 3p plus 2 does not exist, no? So if it is 3p, we will have 3 orbitals. Those orbitals are labeled as -1, 0, +1, 1. So therefore that is wrong. So answer for the first question is going to be Roman number 2. Right, then look at the next one. Of the 3 ions, sodium plus, potassium plus, and calcium 2 plus, largest ionic radius. Now these ions are there in the near 4 boxes. So how they are changing? They are changing according to the mirror is sodium plus. Then third one. Of the 3 ions, lithium, sodium, magnesium, which one is the least polarizing power? Yeah. So polarizing power, we haven't discussed that. It will be there in the ionic character. Polarizing power of cations. So it depends on charge and size. If charge is higher, size is lower, then your polarizing power will be high. So the least polarizing power will be therefore the one with the highest charge and smallest. They are asking the least polarizing power. So least polarizing power will be there for the sodium. Now the earlier question they are asking the one with the largest ionic radius, no? So I mixed up the 2 questions. Largest ionic radius is there for the potassium. And look at the fourth one. Lithium, beryllium, boron, which one has the lowest second ionization? Second ionization. These are the first ionization, lithium, beryllium, and boron. So when you go to the second ionization energy, they assume the previous element's configuration. That means it comes to the helium state, and beryllium comes here, boron plus comes here. So least value are they asking? Yeah, lowest value will be there for the beryllium plus. So don't write beryllium plus, just say beryllium. They're asking for the elements. And this fifth one, lithium, carbon, sodium, which one has the most negative value for the electron? Most negative value will be there for a metal, as a non-metal. which is C, because it is a non-metal. Non-metals are more likely to gain electrons than metals. Other two are metals, no? Therefore, it's not having the least value. Carbon is the one with the least value. So not the least, I mean most negative value. The more likely to gain electrons. And the last one, they have given three structures. We did this one during your theory class also recently when we discussed hydrogen bonding. And these three structures, they are asking strongest intermolecular forces. So interestingly, they all are having H bonds. They all are having H bonds, right? So then how do we compare the strength? They are having same H bonds. So you can compare the strength using the London forces, right? So this is having more size. So therefore it will have more London forces. London forces are higher. Okay. So therefore the strongest intermolecular attractions are therefore the third one. CH3, CH2, CH2, both. Write the structure of that compound. Okay, Lama. I hope you understood that first part really well. Then let's see FBRO3 Lewis structure. Now, in this question, Lamai, they haven't given you a skeleton, which means you need to figure out the skeleton using the electronegativity values. So least electronegative element, which is bromine here, will be the central atom. Yeah, so let's get the structure. Fluorine always makes single bonds. Now to cancel any charge, yeah, then bromine will not have any charge, no? Bromine has 7 electrons. So this is the Lewis structure. Very easy. 1, 2, 3, 4, 5, 6, and 7. Then it's asking the shape and oxidation number around the central atom. Our central atom is bromine. Shape, you can say tetrahedral. Tetrahedral, so no lone pairs. And oxidation number, they all are pulling electrons away from bromine. No? So it's going to be +7. They have given you this structure and asking you to draw resonance. This is less stable, but others, see, they are unstable. When you change the location of the 5 bonds, then obviously you will get unstable ones. So there are many structures. So in this page, you have 12 structures. And there is another page also. In that also you have 12 structures. So there are 24 structures given. So you can take a screenshot of this one, no? You can keep for the studies. No? Go to the other one. This one is the next page. Okay, study them. You can violate octet, you can keep the octet because the structure given in the paper has violated the octet for the sulfur. Then you can keep the octet for the sulfur and draw. Then you will have more charges. So because of the high charge distribution, then it is unstable. Then when you try to minimize the charges and keep the 5 bonds in different locations, then you will have positive charges for oxygen. Again, it will be unstable. So like that, think. Okay, Lama. So that's kind of manageable. VSCPR thing. I'll just say the answers for this one. And yeah, for carbon, C1, it is having 2 VSCPR pairs, a triple bond and a single bond. 2 VSCPR pairs, electron pair geometry is linear for that carbon and shape also linear, and hybridization will be sp. Then you go to the N2 nitrogen. N2 is having 2 bond pairs and 1 lone pair. So 3 VSCPR pairs for the N2. An electron pair geometry trigonal planar. Shape is going to be angular. And hybridization is sp2. Okay. And C3 again, 3 repulsion units. So no lone pairs, therefore shape and geometry, electron pair geometry, both going to be trigonal planar. And hybridization is sp2. N4, you have a lone pair and 3 single bonds. That means 4 repulsion units. 4 repulsion units. So it is having tetrahedral electron pair geometry. Since it is having 1 lone pair, shape is going to be trigonal pyramidal. Okay, and hybridization is sp3. Hybridization is sp3. Like that you can manage, so can do it now fast. Then here they're asking for the orbitals that participate for the sigma bonding and phi bonding. I'll show you the marking of that part. So N and C1, 2p, or you can say sp also, because there's a triple bond no, between the first nitrogen and the carbon. sp or 2p then sp2, like that you can write. So where you have hydrogen atoms, remember to add 1s. If you have completed this one, you can add now marks. So in this here also, the the 5 bonds are made between carbon, nitrogen, and those elements. So therefore, their orbitals are going to be 2p. And they are asking about the bond angles. Yeah, C1 is a linear. So then the bond angle is going to be 180 approximately. Then N2 is going to be, yeah, trigonal plane with lone pair 117.5. You have to subtract 2.5 from 120. And then C3 again 120. So no lone pairs. N4 107 degrees. From 109.5, we are going to subtract 2.5. Because it's kind of similar to ammonia. And then they're asking the increasing order of the electronegativity. What you have to do there, first take carbon is less electronegative than nitrogen. Okay, so C1, C3 are less electronegative. And N2, N4 are more electronegative. So then compare between the carbon atoms. C1 is sp hybridized. C3 is sp2 hybridized. So S percentage is higher when the hybridization state is sp. Okay, so least electronegative atom will be C3. Then C1, high electronegative. Then you can apply the same theory for N2 and N4. N4 is less electronegative. N2 is the highest electronegative because it is sp2. The order is C3, C1, N4, N2. Like that you can get marks for those answers. And then they're asking a really interesting question. Now they're asking you to explain. An acceptable Lewis dot dash structure cannot be drawn for OF4. They are telling that this statement tells you can't draw a proper structure for OF4, Lewis structure. Then you need to say whether it is true or false. Right? For telling whether it is true or false, you will get marks separately. So this one is actually that is true. Why you cannot draw? Why? Then just try to draw Lewis structure, you will realize that. So when you write the explanation notes, you have to show. If you try to draw the Lewis structure, this is how it's going to be. A lone pair with 4 fluorine atoms. So now around oxygen, you have 5 repulsion units. 5 VSCPR units, but that means octet is violated, no? So oxygen is a second period element. It can't keep more than 8 electrons. So it must follow the octet rule. Therefore, this is going to be wrong. Understand? Therefore, this is going to be wrong. So let's see the marking that they have provided for us. Electrons around the oxygen. You have to draw the structure. For drawing the structure, you will have some marks. You can see for telling it is true, you get 3 marks. For drawing the structure, you get 3 marks. Okay? And then you have to say that the structure is wrong. That could be said by telling the number of electrons around the oxygen, or you can say exceed the 8. Oxygen is a second period element and cannot exceed the octet. The same thing is there, no? Yeah, okay. And therefore cannot be drawn a acceptable structure. And then there is another question on electronegativity. They are asking whether the electronegativity increasing order is this. NBr3, NO2Cl, HNO2, and NO2 plus. So if you go with the structures, NO2 plus is this. HNO2 is, and then NO2Cl, this one. NBr3. This one is a lone pair. Okay, so first of all, we are comparing the electronegativities using scope, no? This percentage, charge, oxidation number, peripheral atom, electron. So this one is having a tetrahedral electron pair geometry, so sp3. That means 25% S caret. This one is having 33.3% S caret. This one is also having 3 lone pairs. So 33.3 S caret. This one is having 50% S caret. Therefore, the order, this one is the highest. That's true. This one is the lowest. That is also true. Then you need to compare between these two. To do that, you need to go for the second factor, charge. If you go for the charge, this one is having +1. This one is having 0. See, that is wrong thing. You have to change these locations. This is wrong. Depending on the charge. HNO2, you don't have any charge on nitrogen. But NO2Cl, you have a charge on nitrogen. So it should be more electronegative NO2Cl. So they have said it is the other way. It's not the more electronegative. It's a clever statement, right? So like earlier, you have to say it is false. You have to say it is false. Then say why it is false. Like I see, similar thing, no? You say the hybridization, charge, ne? Higher this character, higher the electronegativity. Higher the positive charge, higher the electronegativity. Then you have to say the correct order is this one, NO2Cl. Then you will get marks for each. So telling hybridization, telling charges, you can get 2 marks per each, no? And first of all, tell it is false, okay? For that, you will be getting 3 marks. Like that, you can now understand, Lamai, what are the questions came for the part C. There is a very variety of questions are there for the part 3, ascending order. And then in earlier questions, there were like asked about the intermolecular interactions and quantum numbers, even photon energy finding things. There are lots of things came in the last part C. And these are the answers for the first part. I won't show you the marking scheme. These are the answers. In the first question, either you can write 2 or you can write the quantum set. That's okay. Yeah. This is the Lewis structure. For the Lewis structure, remember to put lone pairs with it. And tetrahedral plus set. Yeah, we discussed. Okay, so I hope it is clear to you that we did today 2022 and 23 structured essays. Okay, so next week we will do 2024. And yeah, write a good review for these structured essays. Most of the things you are already learned. But if there are any case, let's say you will get a few questions wrong, then write a small review for them. That will be it. Okay, and there is a test coming up at the end of this month, so let's get ready for that. And more importantly, try to practice now the new lesson we are starting, the chemical calculations. Okay, so in this week also we will be doing some part. We'll see. Little by little, you will get there. Okay, right. So I hope you all understood today's session. So good night, everyone. Study well and see you again in the next class.